Last week was an insane week to be a space journalist. Crammed into 6 days were the following. On Saturday, Congress finally passed the FY 2024 budget for NASA and the National Science Foundation, with funding cuts. On Monday, President Biden released his FY 2025 budget request, and NASA Administrator Nelson did his State of NASA address. While that was taking place in D.C., the Lunar and Planetary Science Conference was getting started in Houston, with hundreds of talks and posters about the latest planetary science results. And in the mix, NASA announced Maven, Juno, and Chandra are all getting shut down. Then announced Veritas is being put back in the budget, and there's science funding associated with the Artemis program. And then, SpaceX launched a super large rocket that died in still unknown to me kinds of ways. Last week was a lot. And the big takeaway I had was this. When it comes to a lot of NASA programs, to be a success, you must not just achieve all the goals that you stated, you need to surpass them by miles and days and stay at the forefront of media attention, or you get canceled. Meanwhile, on the commercial side, you just need to do something new to be cheered on as a success. Peregrine made it to orbit. Congrats. Odysseus made it to the moon softly before falling over. Congrats. And SpaceX took Starship above the Kármán line and sent back extraordinary imagery before ceasing to exist over the Indian Ocean. And if you're trying to understand how what feels like a double standard has come to be the new normal, well, like many things, it all comes down to money. NASA is spending taxpayer money and has to report to Congress when things go sideways, and Congress just keeps taking away funding. So the only stuff that can be funded is the extraordinary. Meanwhile, if a billionaire, and there are several to pick from, blows up a few rockets worth of their own money in the name of incremental development, well, that is their money, and explosions are cool, and they let you learn things. And in looking at everything last week, I had one wish. Can we have more honest metrics before projects take flight? NASA needs room to achieve without having to push people into 70-hour work weeks, because overachieving is the requirement. And we need to know before takeoff what are the key things a company like SpaceX wants to learn, so we know we're supposed to celebrate when a 65-minute mission ends early in a giant question mark of, well, our spacecraft is no longer there. As I said before, and as I'm sure I will say again, we need to dare mighty things. We need failure to be an option. We also need to know beforehand, what are the expectations? Last week was a lot. And today we have planetary formation, galaxies at the beginning of the universe, and a whole lot more science to bring you. This is Escape Velocity Space News. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. We live during a great time to be a cosmologist. Between the availability of computer processing and the final completion of JWST, we are able to both see more and model more than ever before. And this is giving us both observational snapshots of our changing universe and the computational ability to figure out what happened between those frames. On the observational side of discovery, two new pieces of data caught my eye. In a pair of papers accepted into Nature and Astronomy and Astrophysics and led by Roberto Maiolini, we have found stuff, the stuff of population 3 stars, those near mythical first generation stars made of primordial material, basically just hydrogen and helium and nothing else. While conducting the JWST Advanced Deep Extragalactic Survey, or JADES, researchers found an actively feeding black hole at the center of a baby galaxy, cataloged as GN-Z11, a baby galaxy shining from when the universe was just 430 million years old. Like many supermassive black holes, this one is a messy eater, and JWST was able to detect a cloud outside the galaxy that is rich in helium and maybe not much else. According to Maiolini, quote, "The fact that we don't see anything else beyond helium suggests that this clump must be fairly pristine. This is something that was expected by theory and simulations in the vicinity of particularly massive galaxies from these epochs. It was predicted that there should be pockets of pristine gas surviving in the halo, and these may collapse and form population 3 star clusters." End quote. This means we have now found population 2 stars, that second generation, that appear to be born from material enriched by just a single supernovae. And we have found the pristine gas that can form population 3 stars. While it was always hoped that JWST would finally find population 3 stars, that hope is now supported by a trail of evidence saying, somewhere in all this data, your stars are hiding, so keep looking. According to an ESA press release, Maiolini and the JADES team will continue their research of GN-Z11 and keep looking for signs of stars buried in all the pristine, beautiful gas. And this isn't the only remarkable galaxy being studied by JADES. It's not even the only one being published about this week. In another paper appearing in Nature, this time by Tobias Lasser as the first author, researchers discuss a galaxy cataloged as JADES-GS-Z7-01-QU. This license plate of a system is shining at us from 700 million years after the Big Bang. And as near as the researchers can tell, it has already stopped star formation and has a light signature consistent with its youngest stars being 10 to 20 million years old. This implies that this system formed, underwent a brief and intense period of star formation, and then just stopped. Just stopped. The word they use is died. But it's only mostly dead, and there's a big difference between mostly dead and all dead. Mostly dead is still capable of coming back to life and forming new stars in the future. According to paper co-author Francesco Diagino, quote, "We're looking for other galaxies like this one in the early universe, which will help us place some constraints on how and why galaxies stop forming new stars. It could be the case that galaxies in the early universe die and then burst back to life. We'll need more observations to help us figure that out." End quote. What is remarkable about all this is the size of the galaxy. It is about the size of the Small Magellanic Cloud, a dwarf galaxy near our own Milky Way that is visible in the southern hemisphere. We are seeing a dwarf galaxy shining from the beginning of the universe. And from 13 billion light years away, we can see it behaving in unexpected ways. As Meolini, who was also an author on this paper, puts it, quote, "Until now, to understand the early universe, we've used models based on the modern universe. But now that we can see so much further back in time and observe that the star formation was quenched so rapidly in this galaxy, models based on the modern universe may need to be revisited," end quote. And this is where I am glad for modern computing power. In a paper that made me do math, researchers have shared out the results of a remarkable new suite of simulations that explore how galaxies are born, live, and evolve. 160 researchers from 60 institutions ran 100 million computer hours of simulations over 8 years. With just 8,760 hours in a year, or a little more than 70,000 hours in 8 years, this means they essentially used 1,500 computers almost continuously for 8 years in the name of science. 3 different papers related to this work have been published in the Astrophysical Journal by the Agora collaboration. The team finds that to reproduce what we see in the universe, including the number of dwarf galaxies and the presence of disk galaxies in the very early universe, it's important to get the gas distribution right. Prior work has always focused on the stars. With this more accurate and complex mass distribution with gas, our more complex universe takes shape in their computer simulations. It also took a lot of work running different models and then rerunning them to make sure everything was right. As one of the lead authors, Santi Roca Fabreja, puts it, quote, "To make progress towards a theory of galaxy formation, it is crucial to compare results and codes from different simulations. We have now done this by bringing together competing code groups behind the world's best galaxy simulators in a kind of super comparison," end quote. This is your reminder. Science is a group sport, and collaboration is required to win the race toward understanding. Up next, we move from galaxies to planets and take in how new data and new models are changing the scale of our understanding. Stay tuned. One of our recurring topics is planet formation is not well understood. And a trio of new papers is making it clear why planet formation continues to not be well understood. Put simply, the universe likes to create solar systems more diverse than an entire planet's worth of sci-fi writers are capable of imagining. Published in Astronomy and Astrophysics, these papers from the Destinies Project look at solar system formation around 86 stars across 3 clusters: the Chameleon 1 and Taurus star forming regions, which are both about 600 light years away, and the significantly larger Orion star forming region, which is about 1,600 light years away. The Destinies Project, which is a clever acronym of Disk Evolution Study through Imaging of Nearby Young Stars, used the super high-resolution SPHERE instrument on the Very Large Telescope in Chile, which allowed them to make out planet-forming disk details in these clusters at the level of being able to see asymmetries and structures associated with large planets. They can also readily measure the size of disks and more. The different environments studied allowed different kinds of stars and solar systems to form. For instance, it was already well known that Orion, which has more mass to form stars, is forming often larger stars. Across these 86 systems, they spotted a few trends. Many faint disks are young, just 2 million years or less in the Chameleon 1 system. Multi-star systems are generally less likely to have large planet-forming disks. In the Taurus system, they note that systems in the core of the cluster are smaller and fainter, while further out systems include both faint disks and bright disks interacting with their surroundings. Both glorious and frustrating, these forming solar systems came in all sizes, and for every trend they found, they also found exceptions. This literally beautiful data set is showing us our planet-forming models need to take into account the density of the surrounding star-forming region, the history of interactions the system experienced, and the elements of chaos theory and statistics that go into explaining when two dust grains will stick together and when they will bounce apart. In modeling our solar system and others, we need to develop algorithms that create worlds like ours on the regular, but also leave space for every possibility to exist. Whimsy isn't a scientific characteristic, at least not in astronomy. But in looking at these images and in trying to grasp what all is possible, I just keep imagining Gene Wilder's Willy Wonka singing Pure Imagination as we imagine traveling to the worlds of all creation, where we'll see things defy all explanation. While the Destinies team is studying the diversity of ways that disks get their start, another team, using the JWST, is working to understand how a planet-forming disk transitions into a disk of planets. In a new paper appearing in the Astronomical Journal and led by Naman Bajaj, researchers looked in detail at the T-chameleon system, a transition system with a 30 AU gap in the center of its disk. This is a gap that in our solar system would reach from the Sun out to Neptune. The gap is showing where dust is already getting removed from the system as planet formation comes to a halt. The system also has gases appearing to be dispersed by a stellar wind. Specifically, they are able to observe a variety of noble gases, gases that don't like to bond into things and that are less likely to get tied up in the forming planets. They see these gases moving out of the disk. Combined, this data paints a bigger picture of a solar system that is pushing out the stuff that forms planets and moving forward with whatever worlds have already finished forming. This star was picked for detailed observations for many reasons, including a long baseline of data over time. Early data from the Very Large Telescope hinted at the gas dispersal and provides comparison data for today's new images. These data sets allow the researchers to see the dying disk change before our telescopes, with dust getting dispersed from the system in noticeable ways across the decades. According to team member Chen Yongzi, quote, "We might be able to witness the dispersal of all the dust mass in T-Chai's inner disk within our lifetime," end quote. This is a new phase in planet formation for our models to understand. As the story goes, gas collapses down into a disk, the disk forms planets, the star blows out whatever gas and dust remains as it finishes its own formation process, and then things happen. In our own solar system, there was an early period of gravitational interactions, flinging worlds to and fro. Understanding that next mystery step, our telescopes aren't quite up to the challenge yet. But we still have plenty of work left to do understanding how planet formation starts and ends. T-Cha is just one star. And if formation teaches us anything, it's that two stars rarely look alike, and we still need a lot more data. When that more data comes out, we'll bring it to you right here on Escape Velocity Space News. For now, it's time for a break. And when we're back, we'll have Erik Madaus for this week's Tales from the Launchpad. Stay tuned. Next up, I'm pleased to welcome on aerospace correspondent Erik Madaus for this week's Tales from the Launchpad. Hello, Erik.
Hey Pamela, it's been a remarkably busy past 2 weeks. On March 4th, SpaceX launched their Crew 8 mission to the ISS from historic Launch Pad 39A at Kennedy Space Center in Florida. On board were 3 NASA astronauts and a Roscosmos cosmonaut.
Ignition, engines full power, and liftoff of NASA Crew 8. Go Falcon, go SpaceX, and go NASA.
Vehicles pitching downrange.
1 Alpha.
Copy 1 Alpha. Stage 1 propulsion is nominal.
The 3 NASA astronauts were Jeanette Epps, Matthew Dominic, and Michael Barrett. Jeanette is the 2nd black woman to go to the ISS and 5th black woman to be a NASA astronaut. Matthew Dominic holds a master's in systems engineering from the Naval Postgraduate School. Matthew Barrett was a NASA flight surgeon working on Shuttle Mir before being selected as an astronaut in 2000. Crew 8 is his 3rd spaceflight. Rounding out the crew is Alexander Gurbenkin. Crew 8 is his, Jeanette, and Matthew's 1st spaceflight. Before being selected as an astronaut, he worked as an aircraft repair technician in the Russian Air Force, including their Swift's aerobatic demonstration team. This was the 5th flight of Crew Dragon Endeavour, a record for the Crew Dragon fleet. The final countdown had a minor drama during closeout, when the crew noticed a hairline crack in the seal around Crew Dragon's main hatch. SpaceX and NASA engineers cleared it for flight in the last minutes of the count, as the crack was small and would be on the cold side of the spacecraft relatively during re-entry. SpaceX has previously flown larger cracks on Cargo Dragon 2 missions on purpose to gather data. This helped them analyze the situation. Launch was successful, with the first stage successfully returning to LZ-1 8 minutes later after launch. Dragon docked to the ISS at 4 a.m. Eastern the next morning. With the relief crew settled into the ISS, Crew 7 successfully returned to Earth on March 12th, landing off the coast of Pensacola, Florida, to conclude their mission. The total duration was just shy of 200 days. A few hours later, on the opposite side of the country, SpaceX launched Transporter 10 on a Falcon 9 from Slick 4E at Vandenberg. On board were 53 satellites.
5, 4, 3, 2, 1, ignition. And liftoff Falcon 9. Go SpaceX, go Transporter 10.
Vehicles pitching downrange.
Doubling. And what do you chamber pressures?
I'll talk about one of those in more detail in a moment. The TLDR version is it carried the usual assortment of commercial, government, and military small satellites into sun-synchronous polar orbit. Repeat customers included Ghost hyperspectral imaging satellites for Orbital Sidekick, flying their 4th and 5th birds on Transporter 10, and 4 Lemur satellites for Spire Global. These carry ship and aircraft tracking payloads and a weather sensor that uses GPS. ICEYE also had 3 of their commercial synthetic aperture radar satellites on board, the 36th through 38th launched, though the 22nd was dead in orbit, so the working total is just 37. Some new passengers for the PY-4 constellation by NASA Ames, a constellation of open-source avionics CubeSats that will demonstrate relative navigation, simultaneous radiation measurements, and do all of this at low size, weight, power, and cost. These spacecraft are designed to measure their positions to an accuracy of 1 meter or better by timing how long it takes radio signals to be received by each spacecraft. The system's radio transmitters are off-the-shelf commercial units. A company that must have heard of how we refer to Starlink missions, has a satellite they call Yet Another Mission. The 6th spacecraft was on Transporter 10. It carries 2 cameras for different science companies to test. On March 12th, Rocket Lab launched another Electron carrying the 4th Strix radar satellite for Synspective of Japan. The launch was successful. No recovery attempt was planned or attempted. On March 13th, the Japanese company Space One launched their Kairos rocket out of the spaceport Key on the southern part of the biggest Japanese island. The brand new rocket carried a small payload for the Japanese government, intended to serve as a quick reaction intelligence satellite. The launch was delayed 3 days prior after high upper-level winds forced a scrub on the first launch attempt. The vehicle exploded about 5 seconds after liftoff, with the bulk of the rocket landing beyond the pad perimeter, where the remaining solid rocket fuel burned for hours. In a post-launch press conference, Space One said the automatic flight termination system was activated, but did not explain why. They also could not confirm if all AFTS charges were fired. It appeared in the live stream that only one on the first stage did. Remarkably, ground-based cameras caught a satellite flying free from the explosion, making it perhaps the lowest orbital deployment ever, if ballistic and by accident count as deployed to orbit. On March 13th, China launched a pair of satellites from the Xichang spaceport towards the moon on a Long March 2C. Called DRO A and B, they were intended to demonstrate navigation around the Earth-Moon system in combination with a third satellite in low Earth orbit, and provide communications links to Chinese missions on the moon. Unfortunately, something happened with the third stage of the rocket, and the satellites were stranded in Earth orbit. It is not known if they can make it to the moon to complete their mission on their own power. We don't have enough time to talk about Starship IFT-3 launch in this episode. We'll go over it in full details in the next episode, when we'll hopefully also have more details on how it went. Before we go, let's take a deeper look at a couple stories. Crew 8 has a busy schedule of science ahead of them in ISS Expedition 71. They will perform at least one spacewalk, originally planned during Expedition 70, but delayed due to a busy February. The spacewalk will replace an S-band antenna on the ISS's truss, used for low data rate, communications, and command control, from the station to the ground. One of the science experiments to look out my eye was H-bond, human brain organoid models for neurodegenerative disease and drug recovery. Neural inflammation is the process of irritation of the body's nervous tissues. It is caused by many factors, including trauma, infection, or autoimmune disorders. It is a significant part of the damage caused by Parkinson's disease and multiple sclerosis. H-bond will carry several brain neuron stem cells taken from real patients into orbit, one set with Parkinson's, one set with MS, and 2 age and sex-matched control sets. The 900 mini-brains will be kept on the ISS for up to 45 days, with some of them receiving an experimental drug every other week. Each week, they will be imaged with a microscope. All of the samples will be returned to Earth for analysis. We're also paying special attention to one particular satellite on Transporter 10, MethaneSat. With a mass of 350 kilograms, it was the largest single satellite on Transporter 10. It carries a special camera to detect methane emissions. It will be used to monitor oil and gas emissions worldwide to reduce climate change. It has a highly precise sensor that provides enough resolution to narrow down methane emissions to individual facilities. The data it produces will be available for free to anyone who wants it, from government regulators to fossil fuel companies and the public. Expect to hear more about the satellite's results in future months. We track launches with the help of RocketLaunch.live. So far this year, the United States has had 30 launches, China has had 11 launches, Japan and New Zealand each have had 3 launches, India, Iran, and Russia each have had 2 launches. Kazakhstan had 1 launch. This makes the total number of launches so far this year 50. Finally, there are 9 toilets in space. Welcome home, Crew 7.
Thanks, Erik. I just want to say how pleased I am to hear that Jeanette Epps finally made it into space. She was selected into the astronaut corps back in 2011 after a highly successful career as an engineer that included earning a PhD at the University of Maryland, working at Ford Motor Company and at the CIA, and even receiving a patent for her work to detect the location of a frontal collision in an automobile. And after becoming an astronaut in 2011, she did a whole lot of really cool stuff that did not involve going to space. In 2017, she was assigned to the ISS for expeditions 56 and 57, but for unpublished reasons, she was pulled at the last minute from launch. In 2020, she was selected for what was supposed to be the 2011 launch of Starliner, which still has not launched. And at 53, she has become the second Black woman to fly as part of a long-duration mission to the International Space Station. And I kind of hope she one day gets to fly again and put all her Starliner training to use. And that's it for now. Good night, everyone. And remember, go out and look up.